The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So this is, I got the preparation for finite elements. Again, we're in one dimension because that's where you can see first and most clearly how the system works. So the system was really to begin with a weak form that I introduced last time, the Galerkin idea that I introduced just at the very end of last time, and that idea is that instead of the continuous differential equation, where Galerkin's idea is how do you make it discrete? And he'll choose some trial functions, those are functions, and some test functions. And I didn't get to say, but I'll say now, very often they're the same. So very often the phis are the same as the v's. So, and probably they will be in all my examples today. And then what's new today is what choices would you make? You have pretty wide choice, but there's some natural ones to start with. And so that's where we are today. And then also the other part of today is how do we get from all that preparation to the equations that we actually solve? The Ku equal F. Where does the K come from? Where does the F come from? The F is going to come, of course, from this, somehow this right-hand side, and the K is going to come from the left side. Okay, so that's the overall direction. If you want to know how finite elements work, that's the key line there. And then here I've recalled what the step was. Here's our differential equation, and there's its weak form. This is the weak form then. Let me put this in. This is, here I've reproduced what we reached last time, the weak form of where that was the strong form with its boundary conditions. Now we get the weak form with its boundary conditions. And the weak form involves U, so it's the boundary conditions on U, the fixed ones that get used in the weak form. The free ones don't appear in the weak form, but by the magic of integration by parts, the free ones will sort of come out in a natural way. But we have to build in the essential Dirichlet boundary conditions like that fixed right-hand end. Okay, and because I think of V as a little movement away from U, but my U's are all fixed at the end, therefore V has to be fixed too. Right. Okay, are you, so this is important, but we haven't made it down to earth yet. We were doing a lot of ideas last time, which are the center of things, but now let's get down to earth. And down to earth really means what functions do we choose? And then how do we get the equation? So that's the job today. It's the principal job, and this is, of course, what you would actually code up to run a finite element simulation. You would make a decision on these functions, and let's start with piecewise linear functions. So a typical phi goes, a typical phi is maybe centered at a node, so it goes up and down. So there is, if that's node 2, yeah, let's number these nodes, 1, 2, 3, 4, and 5. No, 5, well, that's 5 there, but I'm going to have, let's see, what do I have here? I've got, at a typical node 2, I've got that my function is 0, except in the intervals that touch node 2. So here's phi2. Phi2 of x. That's its graph. It comes along, it's piecewise linear up, it's piecewise linear back down, and it's 0 again. So that would be phi2. Then phi1, there'll be a phi1, like so, exactly similar. The whole point is keep the system simple. That's what the finite element idea is. Use simple functions for the phis. And I'm taking them also to be the test functions v. Keep those simple. Now, what about at the boundaries? Okay, well, we've said our functions have to be, I'm doing free fixed. So fixed is, it comes to 0 there, and I've got all my functions will do that. But this end is free, so here's, watch this. This is another, what I'll call a half hat. If I call those hat functions, is that okay? It makes a nice short word. These are hat functions. And then the fuller description would be piecewise linear, but hat functions is clear. Okay, now notice I'm sticking in here what I maybe could call a half hat. Because I don't, my v's and my ph's, my functions are not constrained at that left-hand end. That's free. So there's a phi1, and there's a phi0, and a phi3, and a phi4. So altogether, I'm going to have 5, and I'm started the numbering at 0, I guess. It just happened, so let's accept that. So I'm going to have 5 functions, and and they will also be my 5 test functions. So let me first think of them as the trial functions, phi. So what was the point about trial functions? The point about is my approximate, my finite element solution u of x is going to be a combination of those. Some u0 times the phi0 function up to u4 times the phi4 function. And these are my unknowns, u0, u1, those numbers. I have 5 unknowns, and I'm using hat functions. So I should really, why don't I draw a graph of u of x? So I don't need the words piecewise linear. You see, I have a kind of space of functions. My functions are all, my approximations are combinations of these fixed basis functions. You could call these phis trial functions, basis functions. You're always choosing in applied math a bunch of functions which, whose combinations are going to be, is what you're going to work with. And here I'm making them hat functions. Okay, so what does a combination of those guys look like? I'll even erase the word hat functions. We won't forget that. So what would a combination of, here's the same interval 0, 1, with the same mesh, 1, 2, 3, 4 guys inside. What would, I want to just, it just helps the visualization to see. If I combine these guys, so those were, despite the way it might look, that's one separate function, 2, 3, 4, and 5. And now suppose I take a combination. What kind of a function do I get? How would you describe this, a combination like this of those 5 guys? What will it look like? Between every node, it will be a straight line, right? Because all these guys are straight between nodes. So a typical function will start at this height will be u0 because oh, well, let me draw the thing. Okay, so I'll put u0 a little higher because I want to end up down at 0. So that might be the height u0. Then u1 might be pretty close. u2 might be coming down a bit, coming down a bit, coming down a bit, and ending at 0. So those were meant to be corners in the, that wasn't a very good bit there. Okay. I wasn't meant to be, yeah. So that height is u0. Now notice why. Why is the coefficient of phi naught exactly the height, the displacement at 0? Because all the other phis are 0. All the other phis are 0 at this point. Only this guy's coming in, so we'll only see at this point, we're only going to see even phi 1 has dropped to 0. So we're only going to see phi 0 times u0. So, oh, I should have said all these heights are, we take all these heights to be 1. Might as well. Of course, it doesn't matter because we're multiplying by u's, but so let's settle. They all have heights 1. And this is sort of a key part of the finite element idea. You see, Galerkin, when he created just 2 or 3 functions phi, he tried to follow the exact solution. He had an idea in his mind what the solution to the problem will be, and he wanted to take 2 or 3 functions that would get him close to it. Here we choose the functions. They're in the finite element library before we even know what the equation is or the boundary conditions. These functions are like the hat function choice. And they have this beautiful sort of, they connect to nodes in a way where, in fact, I got involved in finite elements in the first place just to understand what's the difference between finite elements and finite differences. Because the finite elements, as you'll see, are associated with nodes. Phi 1 is the only guy that's not 0 at node 1. And therefore, what will this height be? What's that height? So that's maybe comes down a little. What's this height? u1. It's the coefficient of phi 1 because phi 1 is sitting there. And all the other phis are 0 there. So this height is really u1. And u2 and u3 and u4 and u5 is 0. So that was u1, u2, and so on. Okay, so what I'm saying is, and we'll see it happen, is that this ku equal f equation that we finally get to is going to look very like a finite difference equation. But it's coming from this different direction, and this way allows many more possibilities, gets things sort of more naturally right. It takes less, with a finite difference equation, we had to go in there and decide what it should be. With finite elements, our decision is just the phis. Once we've decided the phis, Galerkin tells us what the equation is. And we'll get to the ku equal f, what it is. But here I'm getting you to sort of see what our approximate solution can look like, and this beautiful fact that the coefficients in here have a physical meaning. They're actually the displacements at the nodes for these simple functions. Okay. You got a picture of what the trial functions are? Some people would think about the functions as these guys. Other people might think of this picture, the combinations. So those are the individual basis functions. That's a typical combination of them, the typical one. Right. Okay. So we're looking for an equation for these u's. 5 equations, of course, because we've got 5 u's. So that's my final step here. What are the 5 equations for the 5 u's? And those are the equations that I'm going to call ku equal f. Okay. So here's now a critical moment. Where do the equations come from? Well, the equations come from the weak form. So I take the weak form, and for u here, I guess it's just there, I put this. I put capital U. So can I just copy? This is the weak form for the, before we've made it discrete, before we've chosen n fees. Okay, now let's choose the n fees. So now this will be the weak form. Again, the weak form. With Galerkin, I mean, after the decision. So it'll be the integral from 0 to 1 of the c of x, whatever it is, times the u of x, times the du dx, right? Du dx. So what is du dx? Oh, you have to pay attention. So now this was the true solution, little u. But now this is where I'm working. I'm working with capital U. So instead of d little u dx, it's d capital U dx. Maybe I'll put it in there, d capital U dx. And then I'll put down here what it is. What is it? It's u naught phi naught prime. Can I use prime just to, or d phi naught dx, whatever? Can I use prime for derivative? Just save a little space. So this is the derivative of my guy. u1 phi 1 prime of x up to whatever it was, u4 phi 4 prime of x. Okay, that's what that term is, and that multiplies dv dx, where v is any test function. Any test function only required to have v of 1 equals 0. But now I'm going discrete. So instead of any test function, I'll use these 5 functions. So I've got 5 functions. The phis are the same as the v's then. v1, v2, v3, and v4. Same guys. So now I'll put in dv. Can I say dv I dx, and on the right-hand side I have the integral from 0 to 1 of f of x vi of x dx, and I is 0, 1, 2, 3, or 4. I've got five different, I'm testing against 5 v's. So I have this equation for five different v's. So I equals 0, 1, 2, 3, 4 give me my 5 equations. Here are my 5 unknowns. This is my 5 by 5 system. Let me just step back a minute so you see what happened there. So what do you have to do? You chose the functions you wanted to, the basis functions, the phis and the v's. Then you just plug into the weak form. You plug in du dx is coming from there, so this is du dx. You have to plug in dv dx. You have to do the integrals. That's something we didn't have in finite differences. Finite elements involves doing the integrals left side and right-hand side. Okay, so and here we have 5 different integrals to do. We have f of x times each v. This number will be f sub I. So my f vector is going to be an f0, f1, down to f4. The 5 guys that I get from these 5 integrals. All right. And the K matrix is sitting here somewhere. That's the last thing, that's the final thing, is to see what is the K matrix, which is coming. This is somehow K's times U's are sitting here, F's are sitting over there. So maybe good to see the F's first. So do you see this now? We made the choices. Then what's our job? Our next job is to do all the integrations. Integrate my function against v. Let's make the natural first example, let f be 1. Okay. First example, let f be 1. All right. So if f is 1, I'm going to do these, I'm going to find the system ku equal f. So if I know f of x is 1, then I have everything I need to find these numbers. Okay, actually, we can probably do those by you can probably tell me what they are. If f of x is 1 now, for this, so this is example 1, f of x is a constant, the one we have solved before. What's the integral? So what's the integral of v0? Right? That's what I have to do. What's the integral of this f of x being 1? I'm just asking, I just have v0 of x. The integral of v0 of x, and let me again draw v0, which is phi0. It's that function that just, it's a half hat, and then it goes along at 0. What's the integral of that function? 1, yeah. How do I think about that integral? It's the area of the triangle. It's the area. That's what integral is. It's the area. So the area is, I've got delta x there, right? Delta x as the base, 1 as the height, and let's see, the formula for the area of a triangle, it's got a half in there somewhere, right? A half. Okay. So it's, can I factor out the delta x, because the delta x is going to come in? I think there's a half there. And then what about f1? What's the integral of this times v1 of x, the next v? It's the area under this dashed function, which is now the base is 2 delta x, so I get a 1. Is that right? I get a 1, 1, 1, 1. Okay, so that was obviously not too tough, right? That was straightforward. And notice something. Notice something. Even here, in fact, we see it here. I don't know if you remember about that half. Do you remember something about when we did finite differences and we had a free boundary and we lost an order of accuracy if we didn't do it right? You remember that? That at the fixed boundary we were fine, but with finite differences at the free boundary where I was using the matrix T with 1 minus 1 as the top row, I lost an order of accuracy unless I made some change on the right-hand side. Look what's happening. The finite element method is making the change for me on the right-hand side. So the finite element method is going to automatically keep the second order accuracy. Keep the second order accuracy. So that's a key point, that these piecewise linear functions are associated with second order accuracy. Later we'll move up to parabolas, to cubics. That will move up the order of accuracy in a nice way, where with finite differences, we would have had to create new finite difference formulas. Our -1, 2, -1 formula, that was good for second order accuracy. Then we would have to figure out, and the quiz partly started it, what if there's a C of x in there, what do you do? Finite differences, there's more thinking involved. Finite elements is like just press the button. Well, there's a little more to it than that, of course, because it's taking a full lecture here. But it's in the end, it's more systematic, you could say. Okay, so that's the F. Now you're ready for the K. So this is the key part. Okay, so I have to get this thing to simplify. So what am I looking for here? I'm looking. This whole left-hand side should be K times U. So I'm looking to see what multiplies. I'm looking to make sense out of this. What's the first equation? Right. So the first equation, or the zeroth equation, I guess. The zeroth equation, the one that'll run along and have this right-hand side. The 0th equation is the equation when I is 0. It's the equation that comes from testing our weak form at for V0, for that particular form. So maybe I'll just start over on this board. I'm just figuring out, and then I can write a formula, but I'd rather you see how it comes. So I'm looking at equation 0. Okay. So take I equals 0. So I have my left side is my integral of c of x times this combination that I wrote, u0 phi 0 prime plus u4 phi 4 prime times dv0 dx equal, and on the right side is where I got the f0, which I already figured out to be delta x times a half. It's the left side that I'm worrying about. Okay, do you see what's happening here? This is some matrix. Its 0th row is what we're finding, multiplying u0, u1, u2, u3, and u4, equaling the f vector. I'm supposed to be getting the first row of the matrix, the top row of the matrix, from the top V. Okay, so let's just do these. We've got integrals to do again. All right, what is dv0 dx? Yeah. Do you see? Oh, let me just see. What number is going in here? What number is going in there? Yeah, if we see that, we're golden. What number is going in there? That's the thing that multiplies u0. In the first row, that means I should use v0. So let's call, this is the point, this is k00. And what's its formula? You realize I'm starting to count at 0 because all these counts. So what is k00? It's an integral of what? C of x, good, times this guy, because it's multiplying, times this guy, v0 prime, dx. That's what you have to do. That's what you have to do. C of x times phi prime times phi 0 prime, that's what would sit there. And maybe well, let's figure that one out, shall we? I have to know c of x, right? That's part of the problem. What would you like me to choose for c of x? 1. Thank you. Okay. I'll choose 1. All right. Let this be 1. All right. Or I could make it capital C, and you would see a capital C appearing everywhere. But let's make it 1. So what are we doing now? What's our equation? Our right-hand side is 1. Our c of x is 1. Our equation has reduced to minus u double prime equal 1, the first equation in the course, right? So we're back to September the 3rd or whatever it was, but doing it now by finite elements. Okay, so let c of x be 1 and tell me what this integral is. So c of x is now, we're taking, in our problem, we're supposing it's 1. Let me just say, suppose it's some function. Then we have an integral, we have lots of integrals to do involving that function. And we might not do them exactly. That would be all right. It's certainly totally okay to do the integrals approximately because we're doing everything else approximately. So we just have to be sure that we do the integrals with sufficient accuracy so that we don't lose accuracy in the integrals. But I don't need, of course, with a 1, we're going to do the integral exactly. But if c of x was some variable function, I wouldn't have to do it exactly. I would just have to do it with enough accuracy so that I don't lose extra accuracy beyond what I'm losing in the whole Galerkin approximation. Okay, ready for that number. What number comes out of that? What phi 0 prime is, let's graph phi 0 prime. And of course, it's the same as v 0 prime. So can I put a little graph here? Here is 0 to 1. And I'm going to graph phi 0 prime. So what's phi 0 prime? Oh, it's negative, isn't it? My little graph isn't going to work. I didn't leave enough room. It's negative, yeah. So, yeah, well, so I'll just write it in words. It's the same as v 0 prime, and what is it? Tell me what it is. What's the derivative of that function? It's what? Negative 1. Wait a minute. Yeah, it's only going to be, it's going to have a certain value. Yeah, you can tell me what it is beyond that point real fast. So it's something up to delta. Well, yeah. So what is the slope? What's that slope there of phi 0? It's not negative 1. It's because, remember, what's the base here? That's not the point 1. I'm sorry. That's only all these were delta x's. Those were just numbering the nodes, but it's the actual length scale is the delta x scale. So now tell me what it is. The derivative is negative 1 over delta x, right? It dropped by 1 when it went across by delta x. And this is only up to node 1, up to delta x, and then 0 afterwards. This is a key point, that all our functions are local. Our functions are local. What does that mean? You can tell me what am I going to get when I integrate, for example, when later on I might be integrating phi 1 prime against v 4 prime. What's the answer? This is the key point. Later, when I'm looking for the 1, 4 entry, when I'm looking there, I'm going to do an integral of phi 1 prime. So let me I'll erase for a moment and do this in my head. When I integrate phi 1 prime against phi v 4 prime, oh, maybe it's maybe it's the 4th row and the first guy over. Maybe it's this guy I'm doing. Doesn't matter a whole lot. Because the answer is, when I integrate phi 1 prime against v 4 prime, it's nice to get the easy ones. It's 0. Why is it 0? Why is the integral of phi 1 prime against v 4 prime 0? Because these phis are local. Phi 1 prime is only non-zero here. V 4 prime is only non-zero over here. The two don't overlap. One is 0 wherever the other, anywhere one is not 0, the other is 0. So that's a 0 there. In fact, our overlaps, I'm just sort of looking ahead here. Our overlaps, a phi overlaps itself, of course, and its right-hand neighbor and its left-hand neighbor, but nobody 2 or 3 or more away. I think our all our integrals are going to be 0 outside. We'll have another tridiagonal matrix. We're going to have zeros all here, and we'll only have entries where of phi against v when they're either the same or just differ by 1. So we'll only have 3 diagonals there. Okay, we were about to find out what that number is. So the slope of this is minus 1 over delta x. And that's, oh, now I'm sorry, let me go back to 0, 0. Okay. This is what we're keeping our fingers crossed for. What's that number? So I have this thing. Actually, is it just squared? That's the slope. And then I want this, and the phi and the v are, I'm choosing the same. So that's the slope again. I think I'm just getting 1 over delta x squared for that times the 1. So what's k 0, 0? 1 over delta x. Why? Where did the delta x come from? Because we're only integrating over, we're not, I mean, it looks like 0 to 1, but they're all 0. We're really only integrating, the only reality was out to node 1, out to delta x. Do you see that the number there, so the number here on the diagonal is 1 over delta x. Okay, how about doing k11 for me? So again, now these guys will be the same guys. It's a square. Now it's the integral of phi1 prime against v1 prime. They're the same. And what is phi1 prime, which is the same as v1 prime? What's the derivative now? It's, what's the slope of this function? It goes up and goes back down, right? I have a plus part. So the slope going up is the 1 over delta x. And then the slope coming down is minus 1 over delta x. So this was up to delta x, and then to 2 delta x, and then zeros. That's a much more typical thing. The slope goes, the hat function goes up to the top of the hat, back down. The slope up and the slope down are easy, and now the integral's easy. So I'm just squaring. Well, when I square it, this squared is the 1 over delta x squared. This is the same, because the minus will get squared. So what's k11? What's k11 now? Have you got k11 in your head? This is 1 over delta x squared. And now what is the integral? 2 over delta x. Because now we're not integrating from 0 to, we're integrating from 0 to 2 delta x, because that's where my functions are going out from 0 to node 2, if the function's numbered 1. So I get, so it's 2 delta x times this. I think we get a 2 over delta x on that diagonal. Would you care to guess the rest of the diagonal? Yes, you'll tell me. What's k22 and k33 and k44? They're all the same. We're just shifting over. So the 2 over delta x goes down there. All right, one more to do. One more integral to do. This next guy. So can you tell me what do I get now for k01? K01. So now this is the case where I am, what am I doing? I'm in row 0, so it should be V0, because that tells me the row I'm in, but phi1. What happens when I integrate? Yeah, just see the picture here. Let me just draw it small. Phi1 prime, so let me draw phi1 and V0. Okay. So, but it's the derivatives that I want. It's the slopes that I want. Okay. So what do I get from here on out? 0, because this guy only got to there, right? The half hat, the first guy stopped at delta x. So whatever is happening here is going to be multiplied by a 0. So it's just here. One delta x interval for this one. And what do yeah, they just overlap in one interval, of course. This guy and its neighbor only overlap in one interval. And what's the deal about the two slopes? They're opposite. One's coming down, one's going up, but the slopes are 1 over delta x and minus 1 over delta x. Do you see what's happening here? I'm integrating. Here I have a slope of 1 over delta x, and here I have a slope of minus 1 over delta x. So I should multiply those, minus 1 over delta x squared, integrate. What goes in k01? What's that number? What's that number? It's that times that, integrated, but now the integral is only going really out to delta x because basically I'm just stopping there. So but there's a minus now because it's not the square, it's this times its neighbor. One's going up, one's going down. So it's delta x squared, and then the length of the interval. This is a minus 1 over delta x. Would you care to guess the rest of the matrix? What's the rest of that diagonal above the main diagonal? It's all the same. That stays the same because when I do phi2, v1, my picture is just like shifted over, but I still have one coming down and one going up. When I do phi3, v2, same thing. And if I do phi1, v2, it'll be the same. I'm going to get this minus 1 over delta x all the way on that diagonal also. Symmetry it's going to come out symmetric. Actually, since the course started by speaking about properties of matrices, let me just say, K is going to turn out to be symmetric, positive, definite. And what's more, for this example, we recognize K completely. You will say, why did you take so long to get to this result? K is the 1 over delta x part times what's the matrix? It's T. It's T. So it's 1, minus 1, minus 1, 2, minus 1, minus 1, 2, minus 1, minus 1, 2, minus 1, and I guess we had 5 of them. Oh, but nobody there, right? That's not there. That fixed, why do we not have a minus 1? Because we've got there isn't a 6. That would be column. We've got 1, 2, 3, 4, 5 columns. There's no U5, there's no V5. We've got them all. And the F, so KU, this thing multiplies U0 to U4 to U4, and it produces F, which is the 1 over delta, which is what? Oh, delta x is in the numerator, right. Times a half, 1, 1, 1, and 1. That is the finite element system KU equal F. For this simple problem. It's exactly what finite differences did. So you can see why my first introduction to finite elements was with the question, what's the difference? The finite element community at that point, this was this was like the golden age of finite elements. All this was just beginning to be created. These elements were being used, especially in civil and structural engineering. That's where a lot of the earliest papers came out of. And then in a model problem, it didn't look anything new. It looked like our original finite difference matrix. But there were some new things. First, there was this new 1/2 that we hadn't particularly noticed with finite differences. We could catch on to that. Here's a minor difference. You notice that the delta x is, strictly speaking, the delta x is up here then, but when I divide by delta x, then I'm back to the finite difference. I have the 1 over delta x squared. It looks like finite differences again. So everything looks the same. But of course, if c of x isn't 1, or if f of x isn't 1, oh yeah, if c of x isn't 1, then I've got integrals to do. I would approximate those, and I could then come out with something that would look like a finite differences. Let me take our other favorite model problem. What would be the f if, yeah, here's a question. What would be the right side if my vector, instead of being 1, what's my other favorite choice? Delta. Shall I take delta at x minus, let me take delta at x minus a quarter first. Suppose that's my f. Then I've got to change all these guys. And what would they be? What would be the new right-hand side when I have this point load? I have to go back to the integrals, right? I have to go back to these guys. These integrals with that new f, this is now delta of x minus a quarter, times each v times dx. I have to integrate delta of x minus a quarter against every hat function and see what it equals. And what will I get? Yeah, you're going to tell me right away. What are those integrals? It's a point load at node 1 times the v integrated over the whole thing. What do I get? I get a 1, yeah, it's going to, that integral is going to pick out the value at a quarter, right? That's what the delta function does. The spike is at a quarter, has area 1, so it picks out vi at a quarter. Vi at a quarter will be 1 for the, I think we get a 0, 1, 0, 0, 0. Again, a little bit what our finite element, finite differences suggested that we should do. All right, here's one final one for today. Suppose the delta function is not at a node. Suppose it's at 3/8. Or it could be at any point A, but let me just take a typical, a special one where I can do it. Suppose the load is at 3/8. What do I get for the integrals now? So now it's delta of x minus 3/8. The spike is at this point here. That's where delta is now spiking at 3/8. Is that right? Yeah, we had 1/5. Tell me what. Oh, I should have had 1/5 before. Sorry. Change that on the videotape. All those 1/4s were, that 1/4 was 1/5. And now what do I want? 3. I wanted to take a nice one that was halfway. I just forgot what halfway was. Where is halfway there? 3/10. 3/10 now. So delta. So that was before I had it for when delta. So previously was delta at x minus a fifth, and now delta at x minus 3/10. What's the f now? What's the f now? So the spike is right in the middle between 1 and 2. What do those integrals come out to be? If I integrate this delta function times the different hats, what do I get? what do I get? Yeah, I get a 0 for this first guy because it didn't touch that half hat. And then what do I get there? Half. And what do I get at the next one? Half again. And then the other guys it doesn't touch. You see, it automatically does the smart thing. It automatically makes the smart choice. And if the spike was at A, at any point A, then at that typical point A, wherever it is, like there, the spike could be there, then I would have, what would I have if the spike was there? I'd have a little bit of phi3 and a big bit of phi4, and the two parts would add to 1. It would take the right proportion. It would be the proportion, it would, by sort of however much this spike was near there, it would give that extra weight to phi4. Okay. Right, so there is the finite element method. It produced something that you might say, oh, we knew that. But you got to see that it deals automatically with C of x, it deals automatically with f of x, it deals automatically with the free boundary. You see it built in, the solution there is going to take sort of a balance, a pretty close balance of this half hat with this one, and the solution will actually be a pretty close to free. It'll be pretty close to having the right zero slope there. Okay, good.